Let's look at question 6 from the 2025 AP Chem free response. So again, just a disclaimer that the answer key is not posted yet. So there may be some discrepancies between how I'm doing these questions and the answer key. So at least this will give you an idea of my thought process. But if you disagree or if you think I did something wrong, please let me know in the comments. So I'm shown a galvanic cell diagram and it tells me that zinc solid, the electrode will increase in mass, and the aluminum solid electrode will decrease in mass. So that's really important because that'll tell me what the anode and cathode are. So aluminum is decreasing in mass. So here's my solid. And so what this will do is it will break down into aluminum ions and electrons. So in other words, this is my anode where the oxidation occurs. And that's the definition of also an anode, is that it will decrease in mass when it's actively participating in the redox. So in question A, I have to write a half reaction for the oxidation. And so I'm given the actual equation here, but we have to be careful because this is written as a reduction. So I'm going to have to flip the equation and write it like this, that aluminum, the solid, oxidizes. Oxidation, remember, is the loss of electrons. So I need to put the electrons on the product side. Okay, so if I flip the equation, my products are aluminum, the ion, and my electrons over here. Okay, so that's how we do A. Now, before we move on to B, if the aluminum is oxidized, then we know that the zinc, this is my cathode, where the reduction occurred. And although it's not asking us to show it, zinc ions here will combine with these electrons. The electrons are going to travel up and across. And whenever they get reduced, I'm going to form more zinc. And so that's what makes the mass go up. I'm going to create more zinc solid according to this equation over here, this half reaction. Okay. So in question B, I have to write a balanced net ionic equation for, so we did A, sorry. We have to write a balanced net ionic equation for the overall reaction. So I can tell from the data that's given to me that the electrons are not balanced. So I can't lose 3 electrons on the aluminum side and then gain 2 electrons on the zinc side, right? So we have to balance our electrons. So if we multiply these together, I'm going to multiply the zinc equation by 3 and the aluminum equation by 2 to give me 6 electrons total. So when I do the multiplication, this will give me 3 zinc ions plus 6 electrons produces 3 zinc solid. And on the aluminum side, again, I have to flip this because it's the oxidation. So this is going to be 2 aluminum solids produces 2 aluminum ions and 6 electrons. So the net ionic, we have to add these up. We get rid of our electrons in our overall balanced equation because they're on the left and right, so they're oxidized and reduced. So they're not in my overall equation. My overall reactants are 2Al solid plus 3 zinc ions produces 2 aluminum ions and 3 zinc solids. Hopefully you can see that, but that's my overall balanced net ionic equation for question C. Actually, this equation will be very useful in part C, so I actually already rewrote it underneath. So I'm being asked here that if I have electrodes, they're both at 50 grams, and then I'm running the galvanic cell for a while, which electrode's mass will change more? Justify with a calculation. So, okay, actually, sorry, I forgot the coefficient there. So I have my balanced net ionic equation, and I remember that aluminum is the anode, so it gets consumed, so its mass will go down, and the zinc's mass is produced, so its mass will go up. Okay, so this mass will increase, this mass will decrease. So, okay, that's fine, but if I actually look at the mole ratio, I can tell that the zinc is probably going to change more, because for every 3 moles of zinc produced, 2 moles of aluminum are consumed. So in other words, there's a greater mole ratio for my zinc product. So let's follow it up with an equation or a sample calculation. Let's pretend I have 1 gram of aluminum that's reacting, that's getting consumed. So if this is 1 gram that's getting consumed, my moles will be 1 gram divided by 26.9 grams per mole. And this will give me 0.037 moles of aluminum reacted. So I'll do a mole ratio to figure out how many moles of zinc reacted. So this is how much aluminum I've reacted. Then I'm going to set up my ratio. I'll put the moles of aluminum on the bottom so that cancels out. I'll put my moles of zinc on the numerator. That will give me my answer. And in the ratio, again, I know that every 3 moles of zinc produced, I use 2 moles of aluminum. So that will give me what? 0.0556 moles. Again, so just my rounding may be wrong, so double check the answer key to see how they did it. So I'm going to change moles to mass by rearranging my mole formula. And the mass will be 0.0556 moles of zinc times zinc's molar mass, which is 65.4 grams per mole. And we can also see that zinc has a bigger molar mass too, right? So that means for every 1 gram of aluminum I consumed, I created 3.64 grams of zinc. So from this calculation again, so I used 1 gram of my reactant and I produced 3.64 grams of my product. So therefore zinc's mass changed more. Okay, and then I won't write down anything else, but I used the calculation and for my justification, and then I did answer the question. So hopefully that would make sense. And again, if you disagree, please put it in the comments. Okay, final question in part 6 is I'm shown a bunch of standard reduction potentials. So these are the voltages that are either required or produced when these ions are acting as reduced species, so when they're gaining electrons. So I can see that gold is a spontaneous reduction, and then all of these other ions, they are negative, so these are non-spontaneous reductions, so they prefer to be oxidized. Okay, so what I have to do here is calculate E cell, so the standard cell potential. So it's telling me that the zinc aluminum one we looked at before has a E cell of 0.9 volts. So I have to create a different galvanic cell using zinc and one of the other options from the table to make the maximum voltage. So I already know I have to use zinc. Okay, so we have to use this as one of our half reactions. And because it doesn't say in this part, like I said, because the zinc E value is negative, this will be my oxidation, okay, because it's more spontaneously oxidized. And then, so I'm not using any of these as my anodes, so we can pretty much get rid of those. So that means the only thing left is gold. Gold will automatically be my cathode. And so I'm going to plug these into my E cell equation. I know there's different versions. I like to use this one, E of the cathode plus E of the anode, but we have to flip the anode sign. For example, E of the cathode, if gold is my cathode, its standard reduction potential is 1.50 volts. And then E of the anode, okay, so here it's written as a reduction, but I'm not reducing zinc ions, I'm oxidizing it. So because I flipped the equation, I'll flip the sign and add. So therefore, I'm going to call E of my anode positive 0.76 volts. And that gives me 2.26 volts. That's the maximum voltage I can create when I use zinc as my oxidation and when I use gold as my reduction. Let me know what you guys think of these answers, and hopefully you did well on this part, on this question on your exam. Thanks.